talk about the Recontech 1312 CNC milling machine, which you can see over here in the room. And so it's one of the most dangerous machines here at the Fab Lab, but we have a nice setup, so it's actually locked. So it's built into or let's say a room is built around it in order to provide as less damage as possible. So it's also soundproof. And so it is basically a milling tool that is mounted on an XYZ axis. And so it can rotate the tool around its axis, and then it can move it in 3 different directions, basically X, Y, and Z. So this machine also features a vacuum table. So these vents over here, these are the, so this is where the air flows, so it's being pulled in through these vents over here. There's a vacuum pump over there on the other side of the machine. And then for the vacuum activated surfaces, so the machine, it actually has 2 sides, the left one and the right one, and those can be activated separately. Then over here to the left, that's the machine controller. So you use this to control the machine. And then the machine controller is connected to the computer. So this is just a screen and a keyboard of the computer. The computer is actually here on the other side, which then connects to the machine controller via a network, so with an Ethernet cable. And then on the computer, you load the G-code, and then this G-code is being sent over, or like the commands, the machine-specific commands are being sent to the controller, which then drives all the motors of the machine. So here we see several tools, and you should be able to tell the difference between those. Actually, let's organize them from left to right. So this is a drilling tool, and this is a drilling tool for wood. It can go only vertically. So you cannot use this for milling. So, or, you know, if you know what you're doing and you need to drill only holes, then you can use this for drilling holes in wood. This other one, with a pointy tip, is a metal drilling tool. It also can go only vertically, so it is made in a way that it is very good at pulling chips out and kind of drilling holes. Also, if you're drilling holes in metal that we don't do here at the lab, because the chip extraction system is designed only to accept wooden chips. So then you would use this only to drill vertically. What we are going to use though is milling tools. So this guy is, for example, a 2-flute flat end milling tool. And it is very good at going sideways. So milling tools are designed in a way that when they spin, they are very good with picking up material on the sides. And this you can use to do cuts and also engrave things on the so on the surface of the material, or like you can cut and engrave the material, but it's not very good at going downwards. So if you're going downwards, then it's usually better to do it in a circular motion, because it needs a little bit of space in order to be able to chip into the material. It's not very good at chipping the material vertically. So yeah, so forget about these drilling tools. Let's focus on the milling tools. So the next thing that we need to know about is also our material. Yeah, by the way, always, when handling material, especially wood, always make sure that you wear gloves. So we're going to use this leftover piece of wood, of plywood. So this is a pine plywood, relatively soft. It also has a glue that is waterproof, so it's like outdoor plywood. Not a very high quality one, but just enough to get some interesting things done. And I mean, if you post-process it properly, then you can make nice things out of it. And generally, I could repeat once more that with this milling machine we mill wood and soft materials, maybe foam, and then we need to measure it. So let's take care of some of the properties that we will need in the process, in the tool path generation process. So let's start with width of the material. So we'll have it at so it's 304 millimeters wide. So let's write this down. And let's measure its length. It's 122 centimeters or 1,200 millimeters. I will just write 1,200 millimeters. So as there's another thing about the material. So okay, we measured the X and Y dimensions, but we need also the Z dimension. We need to know the thickness of the material. So let's take a caliper and measure the thickness. The thickness is, so even though this is supposed to be like an 18 millimeter plywood, it's showing a different value because it probably was shrinking. So all kinds of things happen with the soft materials. They shrink, they're being compressed, they bend and whatnot. So now we see that it's 17.64 millimeters. So let's write that down like this. So that's for the material. Other thing that we should know some properties about the tool. And if you are interested in more tools, then you can actually find them here. So here's a drawer. So here you can find some tools. So they are labeled with serial numbers. So the numbers, so the first number that you see here, it basically tells you the diameter of the cutting part of the tool. And then if you follow these numbers and then look up on the wall, there's a table which is going to give you more information about the tool. So like for example the flute diameter and then the flute length. So it's sometimes sometimes necessary to set up tool instances in Fusion, for example. Then number of flutes, that's very important. Most of the tools that we have here have 2 flutes. Then shank diameter, that is important for mounting the tool. So yeah, but let's continue with the tool measurement. So this one came into a box that is 8 millimeter 2 flutes flat. So you can of course look up the table, but you could also use the caliper in order to measure its diameter, just to make sure. So sometimes things are not put in the right boxes. So you see it shows 8 millimeter diameter for the cutter and also 8 millimeters for the shank. And then we can also check, what is the flute length. It seems to be 30 millimeters if I'm looking from the right point. Also about this tool, what we can see is that it has a interesting geometry. This is the so-called down cut tool. So when it's going to be cutting, it's going to be pressing the chips down. So it's very good for cutting the thin materials, and also for plywood it is nice to use it in order to cut the top surface. Usually you would, so if you want the cut to be really nice, then you would use this in order to cut the top surface, and then you would use an upcut tool to cut the rest of it, but maybe that's too much detail. So we're going to use this tool. So now we can also write down some parameters for the tool. So basically what we need to know is the diameter and the number of flutes. Also the number of flutes, if you see, so there are 2 flutes if you look from the bottom. So these are the cutters of the tool. So the tool, so it's going to be 8 millimeters and 2 flutes. So this is all the data that we need for now in order to start setting up the toolpaths. Okay, so here we are at the computer. We have all the data we need in order to generate the toolpaths, and for the toolpath generation we're going to use a software called V-Carve Pro. The V-Carve Pro is not the only software that you can use for a toolpath generation. You can also use Fusion 360 or FreeCAD, but the same principles apply to all of them. So for generating toolpaths, you're going to need certain kind of information. We just captured some information about our material and also the milling bit. So we are ready to create a new file, which is going to describe our job. So for the job setup, we're going to choose single-sided for now, so just to stay on the simple, on the easy side. And then for the width, we're going to enter 304 millimeters. For the height, we're going to enter 1,200. And for the thickness of the material, we're going to enter 17.6. And these are going to be millimeters. So in a similar way as for the PCB milling, on the SRM20 or MDX40, you need to set the Z0 position. If for the SRM20 you were setting it on the top of the material, then in this case we're going to be setting it on a machine bed. So given that we are also going to use a sacrificial layer, so we're going to choose machine bed. So this is also going to ensure that the zero position is always at the very bottom of the material. So it's going to be easier to control whether the tool actually cuts through the material. And then XY datum position, so that's the XY origin point. So usually, so in the same way as with the SRM and MDX40, so here the recommended value is the bottom left corner, or the southwest corner. So let's leave it here to try not to use the offset unless you really know what you are doing. So if this is checked, then make sure that it's unchecked. It can cause some issues or some problems, maybe like uncertainties later. And hit OK. So this also assumes that you have some kind of a drawing ready. So you can export DXFs and SVGs and DVGs and Adobe Illustrator files, and then import them into V-Carve. But this time, just to test some things. So we're just gonna make something really simple, also to explore the available tools over here. So let's start with creating a rectangle. And so for each tool that you open here, there's an additional menu. So we can specify really precisely where we want that rectangle to be, and specify its width and height. So let's say we want to have 150 millimeter wide, or maybe 20 is better, like 200 millimeters and 200 millimeters, or let's make some kind of a shelf structure, something like this, like so. Okay, and when you click create, it's going to create the rectangle. It's closed. Let's try to position it somehow as we like, somewhere here in the center. And let's create one more. So with the rectangle tool, you can actually also click and draw in order to create them, the rectangles. But if you want precise measurements, then you can use the rectangle menu over here. So for moving it around, let's select the transform mode, move, scale, rotate selection. Let's try to align it somehow. And what I'm going to do, I'm going to create some features which are going to allow me to snap them together in an angle. So sort of a finger joint thing. If we do not remember what is the size of it, so we can use tools like the measuring tool or like this dimension tool. So we can actually select the point over here and then go over here, and then we can check what is the distance. So this is 200 millimeters. And let's create a rectangle that is going to be 100 millimeters wide. And so here we need the thickness of the material. So it was 17.6. That is going to work as our connector, or like as the finger joint. And we can snap it somewhere. Let's do it like this. I'm just wondering, is it possible also to align those? Yeah, so we can select this alignment tool. Oh, this is vertically. Oh yeah, so here you can align to material. Okay, there are quite a lot of nice options over here, but now we centered them in the material, and we also centered them in between themselves. What we could do, we could also center this one in the material like this. And what we could do, we're gonna make a copy of this one. So edit, copy and paste. And let's move this inside the other object. And let's align those together. So inside edge, we want to align it like this, and then we want to center it within the material, and also, so yeah, within the rectangle and also within the material. We can also double check whether these are aligned properly. Here, first need to select the bigger rectangle in this, and then, no. Yeah, now it's right. And we can close this. And so what we want to make sure of is that these lines are, that there are no lines overlapping. So because we will need to cut out the shape of the object, but you know, if the cutter is going to go somewhere in the middle, then we're not going to achieve what we want. And then for the other one, we want this part to be cut out from the rectangle. So what are we going to do? We're going to select these two and look up this weld option, weld them together. And then we're going to select those two and select the subtract option like here. So now, as you see, you know, the idea now is clear. So I want to snap these together. Of course, you know, if you're using parametric software like Fusion FreeCAD or whatever, then you can define all of those as parameters. You can define the thickness as, of the material as a parameter, and you can also then define the tolerances in between as you read after from the process. Next, I'm gonna create a little circle that's gonna be a pocket for let's say a flower pot. Let's make this, and let's go with 70 millimeters. Small flower pot pocket. And let's use the same alignment method. So we want to it to selection and maybe move it a little bit down here. Okay, and now from here, so we can go back to the main view like this, disable some certain mode. So we need to specify, so we need to generate tool paths so that the machine can understand how to move the tool in order to cut these out. And there are going to be certain things that we're going to bump into. So for example, for this inside cutout, there's going to be a problem that we're going to encounter the problem is going to be the following. So this is the tool when we look on it from the top. So it has a certain diameter. So in our case, it's 8 millimeters. And if we are going to use it in order to cut along the line, then what is going to happen in this corner is this is it's gonna leave a little bit of material, and this is gonna prevent us. It's gonna prevent the sharp corner of the other part to actually fit in there. So we need to make sure somehow that this corner is shaped in a way so that the tool can actually cut it out in a way so that there's enough room for the other part to enter. And V-Carve is nice for that because it has special tools that we can use in order to fix it. And the tools are called, so the main tool that you use for this is the Fillet tool. And for that, we need to enter the tool radius. So we're going to use an 8 millimeter tool. So thus we could specify the tool radius as 4. But I'm adding here 0.1 to the value just to make sure that the tool, you know, sometimes the calculations, if the values are very precise, they do not finish nicely. So the tool generator, Toolpath generator sometimes skips some areas if there are overlaps. So I'm just telling V-Carve that you know, the tool might be a bit bigger, and so we could do a normal fillet if we know that we don't need this extra space for the other part to enter there. You can also cancel it out, or we can use the so-called dog bone fillet, which is going to create the minimum cut necessary in order to make enough space. You know, just to, so now if I close this and let's say I draw a rectangle from here to here, you see that the corner of the rectangle is going to fit right in. Or you can also choose to have a T-bone fillet. So by clicking on the individual on the edges, on the top and the bottom, you can specify where the kind of the T element, like where the cut is gonna go. So sometimes this can be useful. So some people think that it looks better than the dog bone fillet, for example, and the plasma, that's more for you know, plasma cutters. So you can choose one of those. So I'm gonna go with a dog bone fillet in these corners over here. And the same goes also for these corners over here. So again, if you're gonna move the profile of the tool around, you'll see that this is gonna not cut into the corner really, and it's gonna causes problems to kind of connect these two pieces together. So let's go to the fillet tool again, and let's add dog bones also here. And yeah, at this point, I think we are ready to go. I'm just going to delete these unnecessary elements over here. Let's save the file somewhere on the desktop. And for generating the toolpaths, you're going to use this menu. So I like to disable the auto hiding here, and it offers you a variety of toolpath operations. And it also shows you, you know, the material setup that we specified when creating the file. So if you forgot to add something, you can always go back here and redefine some values. You know, let's say you discover that the material that you're using actually is, you know, 1 millimeter thinner or thicker, these kind of things. The toolpath operations that you're going to use at first, probably you're not going to use more than the profile and the pocket toolpath, but you can also use the drilling toolpath if you understand the difference between milling tools and drills and you want to drill only. So we're going to start with the profile toolpath, which you can call also the cutting toolpath. So you click on that. The parameters, so the cutting depths. So it's how deep your cut is going to be for the tool, so the total cut. So start depth, it aligns with the top of the material. Even if you're setting the Z0 at the surface of the machine bed, this is going to be always the top of your material. And the cut depth is, you can keep it the same as the material thickness, but just to make sure that you cut through, you usually add a little bit. So I usually add 0.2, so I'm going to go with so 17.6 plus 0.2 is 17.8. Then for the tool, we're going to choose 8mm tool, but here you go, it's here. And there's a variety of tools. You should choose one of the metric ones, N-mill 8mm. So here you can see also some specific parameters that we captured earlier. So I'm going to use 8mm for the cutting geometry, or the cutting part diameter. Then a pass depth, so that is usually, so depending also on the chip load that you're going to use, so it's either the full diameter of the tool, or I usually like to specify it as half of it, so that's much safer. And then the step over, this is important, for example, when you are clearing a pocket. So how many millimeters or percent of the tool diameter you want to hop over in order to clear some certain area. You can understand more how this works once we generate a pocket clearing toolpath. Then feeds and speeds, this is very important. So this is probably the most important part in CNC milling. So you should really understand a few things about the milling machine in order to be able to calculate about the milling machine, and also the tools in order to be able to calculate this. So here the spindle speed, so it's 16,000 revolutions per minute. And if we look up Recontech 1312 machine, so we find that on cnc.fi, there's a page about it. And then here there are some parameters about a machine. And it tells us that the speed of the spindle is in the range, it can be in the range from 0 to 18,000 revolutions per minute. We're going to take advantage of that. And I don't want to max the machine too much, so that this is why I'm choosing 16, but theoretically it can go up to 18. So let's choose 16,000 as the spindle speed. The feed rate, that's something that we're going to calculate in a second. So feed rate, this is you know, the XY, the speed of the XY movement. And we should also stay in the range of the machine capabilities. So here, so we can go up to 20,000 millimeters per minute. And then the plunge rate, it's the vertical movement. And as we know, you know, like vertical moves with the milling tools are tricky. So this is usually, you know, one quarter or 1/5 of the feed rate. But how do we calculate the feed rate? So the tool that we're going to use, it comes from a certain manufacturer, and the manufacturers, they usually have tables like these, which are specifying the chip loads for certain diameters of their tools and for different materials. So in the same way as with the laser cutter, so take these values you know, as a starting point, and then actually do small tests in order to find out what is the best setting for you. So for the 8mm tool for soft wood, we can choose the chip load of 0.07 millimeters, and so these tools, so this specification is also taking into account the other practical tips that they have in this manual. So probably it's calculated also for the full depth of the, so not full depth, but the depth of cut that is equal with the tool diameter. So it's a bit slower than normally. So we have another table, in this green book over here. But we can use this as a starting point. And this is amount in millimeters that each of the tooth of the tool is going to be cutting per 1 millimeter. So, and then in order for it to cut this certain amount of material, it needs to move forward. So it rotates and moves forward at the same time, and thus it should cut this amount of material. So let's take that into account in our calculation. Another thing that we'll need to know is the number of flutes. And remember from measuring the material there, so looking at the tool there, so we saw that there are 2 flutes. So let's use a calculator in order to calculate the feed rate. So the chip load for the tool is 0.07. Then the number of flutes is 2. And then we need to also know what is going to be the spindle speed, which is going to be 16,000 revolutions per minute. And what we get is 2,240. Let's use this. You can also, like round it up, but let's test with these values and then see, maybe we can improve this. Yeah, for the plunge rate, we could just calculate 1/4 of it. So it's 560 millimeters per minute. So basically, feed rate equals chip load times number of flutes times spindle speed. And in our case, it was chip load was 0.07, then times 2, then times 16,000, and what we got was 2,240 millimeters per minute. So yeah, so we calculated the feed rate and also extracted the plunge rate for it. So now we're all set. So, and we're going to start with half of the diameter pass depth, which is okay. Next is we need to decide how we're going to cut, outside or inside. So for that, we're going to select the shapes that we want to cut. And of course, these we want to cut from the outside. Climb or conventional. So the climb is going to leave a cleaner cut but put more pressure on the tool. But conventional is going to be more aggressive because it's going to cut against the direction of the movement of the tool, but it's going to cause less pressure on the tool. Climb is like climbing a wall. So when the tool is rotating, so you can imagine, you should think about how the tool rotates, and then the cutting edge is going to climb the edge that it has to be cut. So it's going to try to climb the edge that we are cutting out here. And the conventional is the opposite of that. And I'm going to skip the separate last pass. What is very important is to add the toolpaths, the tabs to the toolpath in order to prevent the finished parts to flying out from the material once they are fully cut. So for that you can specify the size, so 5 millimeters, and so it really depends on the material. The more dense the material, the smaller tabs you can actually leave, but the material that we're going to use is relatively soft, so we want to leave bigger tabs. So 5 millimeters, long and 3 millimeters wide. That's fine for now, and we can also edit them. So we can generate a constant number of tabs, and then the V-Carve is going to calculate them for us, but they might not be in locations where we want them to be. I don't like to have them on the corners because it's really hard to then file them away or send them away. So we can delete those, and we can actually just put them manually. So I'm gonna should be okay. And then we can close them. The menu. So ramps and all of this. This is also pretty much you know, like advanced stuff. I'm gonna not gonna cover that. And then here we can name the job. Let's give it a name. Outlines, and hit calculate. Now, so this is a warning. You should pay attention to warnings and read the text, obviously. And what it is telling us is the current tool cutting depth is exceeding the material thickness, which it is. So remember, we set the maximum tool depth for a Toolpath generator to be 0.2 millimeters more than the thickness of the material. And in this case, we know what we are doing. So we're going to use a sacrificial layer, and it's fine to actually cut into this sacrificial layer a little bit just to make sure that we cut through. Yeah, and it's just warning you that if you're cutting on the machine bed, then it's gonna probably cut into it, and we don't want to damage the machine bed, because then you're gonna damage also the vacuum capabilities of it. So you don't want to do that. So, but we're gonna use a sacrificial layer, so it's fine. So we hit OK, and here V-Carve is gonna give us a nice preview. So these blue lines, these are the actual tool paths. So the center line of the tool is gonna move along these paths, and we can preview how the tool is going to cut those. And so as you see, yeah, also with the slowest speed, it's doing it quite slow, quite fast. And you can also see what the tabs are. So these are the tabs, so which on the last pass of the tool are being left, so that the material doesn't jump, so that the parts do not jump out from the piece of material and do not damage the machine, and most importantly, do not harm people. And here you can also see that the dog bones are nicely cut and calculated. And yeah, you can also reset the preview. Let's close this and let's go back to the 2D view, because there's one more thing that we need to do. We need to explore the pocket toolpath. So let's select that. And here, instead of specifying the depth of cut, so we don't want to cut through, we rather want to have a certain depth of the pocket. So let's say that the pocket is going to be 5 millimeters deep, or maybe 7. We're going to use the same tool. Just double check whether you have the right settings set there. And mill. So, and here the step over is important. So 40% of the tool diameter, it's usually fine. Then here you can specify the way how the pocket is cleared. So we can offset it, so it's gonna showing a little preview icon over here that's gonna start from the center and then go in a spiraling way. Or it can also do a zigzag motion and then kind of clear the final edge at the end. And here you can also specify the cut direction, climb or conventional. As I told before, climb is going to leave a cleaner cut. And yeah, so you can also specify what is going to be the profile pass, whether it's going to be at the beginning or at the end. So probably last is generating less stress on the machine. Then ramp, I'm going to leave this out for now. And I'm going to name this operation pocket. I haven't selected any vectors, so this is going to be the vector. And calculate. And zoom in over here. So yeah, you see it has two levels of these Toolpaths, and if we play them back, yeah, you see it's gonna, yeah, so this is gonna, how it's gonna work. And this is pretty much what we expect from the machine. Yeah, now we are ready to export the toolpaths. So we hit close here, so we can select these two, and then save toolpath. And if you're using the same tool, then you can output all visible toolpaths to one file. If you're using separate tools, then you would rather separate them in separate files. And here, yeah, so you should choose the Mac 2.3 arcs millimeter file. So gerbil you can use if you're building your own Arduino-based CNC machine. And we hit Save Toolpath. So I mean, if it's a small job, the name doesn't matter. But if you're doing a bigger job, then usually, you know, what kind of job it is, you could add. Then let's say you're using 8mm tool. You can also use shortcuts as T, 8mm, and then let's say for thickness of the material or depth of cut, you could specify the thickness of the material. 17.6, or you know, material. And this is gonna hint you, especially if you're using multiple tools, then you want to maybe have the tool sizes added here. It doesn't add it automatically like CopperCam, for example. I want to use the vacuum table capabilities, and this is why I am going to open a few vents. And you should kind of also take a look at the material. So now, because of the material size, I can see that the vacuum so the area that could be used for the vacuum to hold the material down could be one of these chambers. So we're going to use the left chamber and then the left side of the left chamber. So half of its potential. So let's open these two vents over here. So this one and that one. And the caps of these, they go into the yellow box just next to the machine. So just put them here. So in case you need also to close the vacuum vents, then you can find these caps over there. And I'm going to close this the cap. So, and I'm going to put this here. Yeah, the quality of the sacrificial layer matters also. So the better the surface, the easier it is going to be for the vacuum to pull the air through. So you might wonder why I'm putting some kind of a material on top of the vacuum system, and whether it's not going to just block it. But MDF is actually relatively porous, and the air is actually flowing through it. And when we're going to put something on it, it's going to actually hold it down because the air is going to flow through it. There are other ways of fixturing. You can use also clamps. These guys. And they are equipped with a T-head. That is so with a special head that is meant for these T-slots over here. So the CNC has also these aluminum rails where you can insert this in like so, and it's not going to lift off. It's going to create a counter pressure for these fixtures over here, so you can actually clamp your material down also like this. But I wouldn't recommend you doing this unless you really know what you are doing. because this includes also, this involves calculating your tool paths, taking into account the fixtures. And so, you know, traveling height of the tool should be always above any of the parts that the fixtures contain, so that when your job starts running, the tool doesn't accidentally crash into the fixture. Or while cutting, it shouldn't also crash into the fixture itself. So with these you should be, so this is an option, but then you should be very careful with it and really kind of make sure that you understand the toolpath generation well enough in order to be able to use it. And the third way, so for the bigger sheets, it might be that you have a little bit of trouble because it's kind of bending. Let me bring another sheet of plywood. So for the spoil board, you would not use this kind of wood. For the spoil board, you would use MDF because the air flows through it. But just for demonstration purposes, I'm going to use this for now. So sometimes you might have trouble with the vacuum table, and you know the plywood is bending, and the clamps do not fit where they should fit. So you could also use some wood screws in order to fixture your object. So you would know that, you know, the bottom layer, so the MDF then attaches to the vacuum bed quite nicely, but you know the problem is the top material. So in order to fixture properly, you could use wood screws and you know, attach them this way, like so. And then just make sure that you do this carefully so that after the job is finished, you can also remove the wood screws.
I guess you'll have to also design the toolpath so they don't need the screws.
Exactly, yeah. So what we did in Barcelona was that we generated a separate set of toolpaths, which would be like a drilling toolpath. So we'd specify points in the Fusion 360 or let's say Rhino design, where we would use for fixturing. And then before running the real job, so we would set the X, Y, Z and everything, we would do this pre-drilling kind of thing. So it would be just 1 millimeter, you know, marking sequence where we would mark where the fixturing holes would go, and then you know we'd move the tool aside, and we would add these at those points, and then you know the toolpath that we generate after it we just make sure that it doesn't overlap with these points. So for safety, I think that's one thing that you could do. Okay, so at this point we are ready to turn on the machine, and then whenever we are doing something with the machine itself, make sure that you remove the gloves. And to turn on the machine, we need to use this switch over here to enable the power supply. Then the next thing is to press this green button over here. Then you should wait for 15 seconds or so. Then on the desktop you should locate the Mac 3 icon and hit OK here. And it's going to open you this interface. And there are 3 things that you should first do before setting up the machine. One is you should reset it. So you hit reset. Then you should always check whether the soft limits toggle is on, so it should have a green line around it. And the third is that you will need to click this button to reference all like the home positions for all of the axes. And at this moment, just make sure that you are at a safe distance from the machine, because it's going to start to move. Okay, so at this point you should be able to move the machine around by using these arrow keys on the keyboard. So you can use the keys on the laptop computer and also on the connected keyboard over here. Just make sure that whoever is walking around the computer outside the room that they do not touch the keyboard while you're working with the machine. So yeah. So we're going to position the spindle or the tool holder at a position where we can easily access it. And now you can see that the dust shoe, or the chip extractor, is actually mounted. So we need to remove it somehow. So, and then there are these two attachments over here. So while holding the dust shoe with one of your hands, just open these, and so that you can slide. So always try to keep control with your hands. Don't drop it, because otherwise this rod is going to just flip outside and he's going to fly away. You're going to fold it around like this, and then up, and then you can fasten these set screws again. So it holds in place. Now we have access to the actual tool holder. And the tool holder has a threaded mechanism, so it has a nut that you can remove, and this nut has sort of a geometry that allows it to hold a thing that we call a collet. And the collet is, we have several collets, and they're going to allow us to actually fixture the tool, so to hold the tool properly. Now if you look at the little drawer, and a little locker over here on the top shelf, you're going to find the collets. And so let's flip them around like this. So from left to right, they're also numbered. These numbers actually mean the diameters of the shafts that they can support. So since we're going to use an 8mm tool with an 8mm shaft, we're going to choose this one over here. So together with the collets, you're going to find also the tools in order to set up the collet together with the tools. So let's take those. Yeah, another thing that is useful is this little soft surface. It's nice to put it under the tool holder, because like if you are doing it the first time, then most likely the tool is going to fall down, and in order to prevent it to get damaged too much, then it's better that it falls on a soft surface. So now also let's take the tool, let's take it out, let's put it here. And very important, the insertion of the collet into this nut. So first you put it in, but you need to apply a little bit of force until you hear a click. And as a result, you should always check whether the surface of the collet is aligning with the bottom surface of the nut. So these should be parallel. So when you have achieved that, then you can put it, screw it onto the tool holder. Do it just enough so that you can, so first until you feel that counter pressure. And at this point you're ready to insert the tool. And so I usually put it 1 centimeter, 1.5 centimeter deep inside of the collet. So now it's kind of, the collet is actually keeping it quite nicely, so I don't need extra movements or anything. And then I would use these keys. So this is a bigger key, like 32 millimeter diameter, to hold the top part of the tool holder. And then this ER32 is the standard for the collets. So I'm gonna first insert it under the nut, and then slide it upwards so it matches with the pockets, so with the grooves of the nut. And now I can do the adjustment. And you shouldn't put too much pressure. So imagine as you would be squeezing a lemon. So and also take into account that during operation the parts are going to heat up, they're going to expand, and after that it's going to be harder to remove them. So I'm going to put the tools back here and remove this, remove any unnecessary objects from the machine. Next thing is gonna be to set the Z origin by using this tool. So here on the side of the machine you can see that there's this Z origin sensor. So you can take that and put it on a location onto the sacrificial layer. And the trick is that the Mac 3, the software, it knows the height of this. So the operation is going to be that we're going to move the tool down, or there's going to be an automatic operation that's going to move the tool down, and as soon as it touches the surface of this, it's probably some sort of a capacitive touch thing, or just a contact. So the machine is going to detect that the current Z location, subtract the height of the sensor from it, and set that as the Z0 position. And in order to do that, we also will need to activate the vacuum pump, because the material is going to be pulled towards the table, and it's going to lose. It's going to be approximately 1 millimeter lower. Also remember that you should use these air protection headphones. Yeah, you should use the ear protection headphones. So because the vacuum pump is going to be really loud. So when you're operating the machine alone or with a friend, so you should never do it alone. So there should be always somebody around when you're operating the CNC machine. So before activating the vacuum pump, also you should make sure of how these valves are arranged. So if they are at this position, both of them, that means that both of them are closed. And then once you turn them in the direction which is labeled as O, means that they're going to be open. So since we're going to use only the left part, we're going to open only the left chamber. So in order to activate the vacuum pump, you will use this toggle button here on the controller. So if you press the button, it's going to turn the vacuum pump on, and if you press it again, it's going to turn it off. Okay, let's turn it on. As you see, it actually lost a millimeter. Now, I'm going to move the machine above the sensor. And here on the screen, you should look for the only finish labeled button, Terran Mythos, and you should press it, and that's going to start the Z0ing operation. You see, look at the Z value. Now it's that button in order to turn the vacuum pump off. So put back the sensor where it belongs before continuing the operation. And then, of course, we can move the tool a little bit away so we have a little bit more room to set up the material. You can use a little bit of compressed air to get rid of dust from the surface. We don't want to have anything in between the sacrificial layer and the material. So again, when handling the material, it's a good idea to wear gloves. So I'm going to pick up the material from here. So you see it's a bit bent, but I think not too much. I hope that the vacuum table is actually going to solve the issue. So let's activate the vacuum pump once again. So now I'm going to activate the pump, and the table should pull the material towards it. this is fine. Let's set the X and Y. So for that, you need to move the tool to the position where you want your X and Y origin to be. And just make sure that, so double check your designs, your toolpath generators, that you have set the X and Y origin, X, Y, and Z origin to the same location where you're setting it. So usually, you know, the left, in the southwest corner with Z pointing upwards, it's the way how you should set it. And when your tool is in the position, then on the interface over here, you just click the 0x button and the 0y button. Okay, and now, just before we are starting to cut, I'm going to remove the gloves again. We're starting to cut. I'm going to move this closer so we can access it. And I'm going to put the dust shoe in place again. So I'm going to open these set screws slowly and carefully and move it here. Set the set screws. The concept of this is, so you see this red dust shoe edge, it actually aligns with the, so it's a bit above the, so the bottom face of the collet. So you shouldn't be worried. So if you have been calculating your depth of cut according to the amount of tool that is out from the collet, then this shouldn't be a problem. And now once this is done, we can actually exit the room and activate the vacuum pump and start the job. So I'm going to activate the vacuum pump. So as you see, the room is quite nicely built so that not much sound is getting through this door and the walls. So this is why it is important that two people are around when operating the CNC machine, because if one of you is inside and something bad happens, you know, it's not, you know, nobody's gonna hear you. So two people always around when operating the CNC machine. We need to load the G-code that we just generated with V-Carve. So in order to do that, you go to the Load G-code option, navigate to where your file is. And so different you know, post-processors or toolpath generators are going to create different files, but essentially they are internally the same. So sometimes like Fusion generates these tab files. So if you cannot find them for some reason, then just remember that you can check the file type over here. And then you hit open, and it's going to display it's going to load the G-code over here, and it's also give you a little preview of the toolpaths, so you can validate it in the context of the machine dimensions. So you see that there's this gray area that is showing the whole work area of the machine, and then the violet cross, it's showing you where the tool currently is. Yeah, and then, or where the starting point is probably. And then, yeah, the blue lines are obviously the toolpaths. So in order to start a job, you will need to use this interface over here. So on the top part, these are only lights. And under the lights, there are two buttons. So when it's green, it means that the spindle is not spinning. When it's red, it means the spindle is spinning, that it's dangerous. So in order to start the job, you're going to press the green button, and in order to stop it, so if you need to stop it before the job actually ends, you're going to press the red button. The red button is also linked to the door mechanism, so whenever you open the door, the job is going to stop, the spindle is going to stop. But still, the spindle has an inertia, so it's going to take some time, 10 seconds for it to completely stop spinning. Okay, so let's start the job. And let's see what's going on there. Okay. So now, as you see, it's the light is green again, so which means that the spindle just stopped. So also you should wait until it visually stops spinning. And then just to make double sure that you are not endangered while taking away, while collecting your parts, you can always use the keyboard and move the tool away a little bit, so it's not in your way when you're trying to remove the material. Now, before entering the room, so that the vacuum pump is going to be on, it's going to be really loud, it's a good idea to use the headphones. So in order to switch off the vacuum pump, you press this button again. So remember to use gloves when handling the material. So, and as you see, the tabs that we put in place, they allow also us to remove the whole workpiece and then just put it aside, so for post-processing. So I'm just going to put it here. And then we're going to, so before you leave the room and before you leave the machine for others to use, make sure that you're going to remove the tool. So do you mean leave the room in order? So in order to remove the tool, I'm going to remove the gloves also. It's dangerous to operate the spindle with gloves because they can be pulled into the mechanism in case it starts spinning, so you don't want that. Yeah, I'm going to move it now a bit closer so it's easier to remove. I'm going to start with the dust shoe. Be careful not to hit the tool with it. And let's use this soft pad over here. Let's get the keys out. And here's a nice trick that I would like to talk about. It's how to safely open up the connection. So how to loosen the nut. So try to keep these two keys as close as possible, so you can grab the handles of those with one hand. It's going to prevent, so in case you're using two hands, you're going to prevent them clashing together. So the first unmounting or unfastening turn can be done like this. So, and then from there you can actually use your hands. Take the tool out. And here, before you're taking it out, so you can see that there's dust inside. So so what I like to do, I like to use this compressed air gun in order to blow in it a little bit, to clear out the dust before I do the removing motion. The removing motion looks like this, so you hold it the top down, no, like bottom up, yeah. And then you press with your thumb. Be careful not to put your nails somewhere in between. So I have seen people who are doing this and then it goes forward and then they break their nails. So try to do it, with the middle of the thumb, somehow like this. And then push it in and put the collet in place. Over here, along with the keys. And don't forget to put the tool back in its box, like so. Close it and put it back where it belongs. So this was an 8mm tool, so put it in the 8mm pocket over there. And mount the collet nut back up like this. And if you have a lot of dust around, then it's a good idea to use a vacuum cleaner in order to clean this up. So I'm going to move this away. So yeah, this is the place where you can find all kinds of sacrificial layers also, and just remember not to put your projects here. So this part is for sacrificial layers only. And lastly, we should turn off the machine. So start with closing down the software. Then press the red button on the machine controller. Wait for a few seconds until this goes up and down and you hear a click like this. And then once after that, you use the main switch and you rotate it to the off position. Okay, let's take our parts, our finished milling job, and let's go to the wood room and let's do some post-processing. So this is the job from the other side, so you can clearly see the tabs over here. So there are several ways how you can cut the parts out. So one is using the chisels that you can see over here. And okay, here's the second one. You can put these on a clean surface. Let's put these in the leftovers part over here. So here in the blue cabinet in the bottom shelf over here, so you can find a tool. So this one, which is basically a router, like a hand router, but we are using it for one specific purpose, to remove tabs. So with this special tool, which has a bearing at its end, and the diameter of the bearing, it's also is the same as the diameter of the tool that we are using. It works like this. Usually use it in combination with this vacuum cleaner over here. You see here at the end of the tool it has this connection over here. So we connect the vacuum cleaner over here so that it can remove the chips that are being cut off by the tool. And as for the power connection, you can use the power connection on this specific vacuum cleaner over here. So it's gonna turn on as soon as you're gonna turn on the machine. So let's do that. Like this. And we also have to plug in the vacuum cleaner itself. Now you're gonna turn on the machine. It's not turning. Here is the on-off switch. So both of these switches should be on the vacuum cleaner. And then when you turn on this, both of them turn on. And then here on this machine you can set the speed. So the maximum is 5, no, maximum is 6, and minimum is 1. So we're gonna set it somewhere in the middle, like 3. And the way it works is that you're gonna use it from the bottom side of the workpieces that we cut, so that the tabs are on the top. And we're gonna place it on the edge, and the bearing is gonna rest on the edge of the actual material, and the tool is gonna cut the reminders, so the remaining tabs. Before we do that, it's a good idea actually to clamp these. Yeah, there's a special way how you hold the tool. So there's this rubber. Woo! So there's this rubber handle, so you should keep one of your hands around it, and then the other hand on the top part of the tool, so where's the on and off button, so you're going to basically control the on and off state with the other hand. And before you turn it on, you put it on the surface, so the little lid over here is going to show you where the tool is actually going. And also you want the tool to be perfectly perpendicular to the surface of the workpiece. So what it did, it's cleared off, these tabs exactly at the level
where the edge is. So it's a very good tool to clean off these edges over here. And of course, as always, after using the tools, just put them back, as soon as possible, so that other people can find them. And then all that's left is a little bit of sanding, so you can find the sandpaper around. So here in the box underneath here, you can use a little bit more rough paper to clean away these. And of course, you can keep going with post-processing those. But one thing that we want to know is whether these two fit together. So this has a really nice tight fit. So if you want to be more loose, then of course you would either modify the thickness of the material or like some tolerances in your design. Basically, we have a little shelf for a flower pot now. One more thing left to do is we needed to calculate whether the dimensions that we have, that we got from cutting it out, they actually are the same as we were expecting. So let me bring the measurement tools and let's check that. And let's first measure this dimension over here. So the expected length of this was 100 millimeters, and we are getting 100.3. So which means that actually we cut a little bit less than expected. So meaning that the tool, it was not occupying the full 8 millimeters as we were predicting or calculating. So the reasons might be because we were using climb instead of conventional milling. So one could actually compare that. So what is the difference between climb and conventional milling? And then another reason could be that just the wood is kind of soft, and while cutting, some parts were expanding and shrinking, but overall it looks like a fine precision. And then this is not, yeah, we can also measure the inner diameter of this pocket. So the expected was 7. Yeah, and here we're getting the same. So the pocket is a little bit. I think that's it for the introduction of the Recontech 1312 or 1312 milling machine. And I hope to see you milling.